This is Lecture 3N for Calculus 1 on related rates. Related rates is an application of implicit differentiation, more or less. So here's the idea. Say you have a balloon that has a certain volume in it, and there's a certain radius to the balloon. When you change the volume, you change the radius, and vice versa. Those are both the volume and the radius change with time. Let me get the highlighter here. Okay, and the volume and radius are related to this equation. Right. So to find out how they're related with time, take the time derivative of both sides of the equation. So here we're going to take dv by dt, and on the other side we take d by dt times 4/3 pi r cubed, and this is what we get. Here was our result. The rate of change of volume equals 4 pi r squared times the rate of change of the radius. Note that there's an r squared term in this particular equation. That means that the volume change depends on how inflated the balloon is, and that makes a certain amount of sense. If you add volume at a certain rate to a balloon that is very inflated, you probably won't see a big change in radius. On the other hand, if you added the same amount, you added volume at the same rate to a balloon that was not even inflated, was very deflated, you might see it a bigger change in radius. We'll put some numbers to this. Say you have a balloon and it's inflated to 3 feet. Okay, this is like a weather balloon or some, I don't know, big balloon. And you want to change the radius at a rate of 2 feet per second. Say you're just sitting on it, you're squishing it, and you're changing that radius so that it's going to go from 3 feet in radius to 1 foot in radius in a second. So I'm going to work through this and find out how the rate that the air is coming out of the balloon. I've got my 4 pi. Then, since the radius is 3, I put the 3 here and square it. Then the rate is 2 feet per second, so I put that here, and I find out that the air is leaving the balloon at a rate of 226 cubic feet per second. What if I do the same thing when the balloon is inflated to 15 feet? Now I have 2 because I'm changing at a rate of 2 feet per second. Okay. The radius is 15, so I put the 15 there. I have to square it, and I get this enormous number out. 5,655 cubic feet per second of air is going to be coming out of that balloon. If I change it from 15 feet down to 13 feet in 1 second. So I'm changing at a rate of 2 feet per second. So see how they're related? And the idea is you set up the equation, then you take the time derivative of both sides of the equation. Here is a summary of the procedure for the related rate problems. First, write down the equation relating the two variables. This equation might contain other variables that change with time. Try to rewrite them in terms of the other two variables of interest. You can only compare two rates at the same time. All right. You might need to use some algebra or the Pythagorean theorem or some trig identities to get all of the rate-dependent variables written in terms of two rate-dependent variables, two time-dependent variables. Then you take the derivative of both sides. You can substitute some measurements into the equation and solve for the unknown. Now I'm going to do the problem of draining or filling a conical reservoir. This was done in the book in Stewart in a couple places, but he always used numbers, like he said the radius was this, or you know, he gave dimensions already, like he specified the big R and the little r, the dimensions of the reservoir. Don't do that. That's not a good habit. Solve your problem just using variables. When you get done, then you can plug in any dimension you want. If you're working with a computer, you can write this up as a little function or a subroutine, and then you can just keep calling it every time you need to solve the problem. You don't have to resolve it. If you solve it using numbers, you don't know how those numbers got buried in your answer, so you'll have to solve it again the next time. Unnecessary. Okay, so here's this conical reservoir. This is the volume. The volume is 1/3 pi r squared times h. R is the radius at the height of the fluid level. H is the height of the fluid level. Now what changes in time in this equation? The volume does, the height does, and the rate does. 3 things change with time. But we can rewrite this equation so we only have two things changing with time by using this ratio. Because the fluid is confined to this this cone, this ratio has to hold. Little r to big R has to equal the same, is equal to big R over big H. I'm sorry. The ratio of R to H, little r to little h, that would be the radius and height of the fluid level, is equal to the radius and height of the outer dimensions of the cone. Now here are the words for what I just said. The fluid is draining, or if the reservoir is being filled, all variables are changing with time. The volume in the reservoir is changing, the height of the fluid level, and the radius at the height of the fluid level. The rate at one variable changes depends on the rates of the other variable. They are all related rates, but you can only relate two at the same time. If you want to see how the rate of volume and height are related, then rewrite the equation in terms of volume and height only. In other words, eliminate the r. If you want to see the rate in terms of volume and radius, rewrite the equation in terms of volume and radius. In other words, get rid of the h. And you do that by using that ratio. Okay, I'll show you how to do that. Here is the volume. Here's the equation for the volume of the fluid in terms of the radius at the top of the fluid level and the height at the fluid level. Now I'm going to use this proportion to write volume in terms of height only. Say I want to compute how that height is changing as I fill or drain the reservoir. Okay, so I can write radius in terms of height only. So here's where the radius was. Radius squared term is right here, and I substitute from this expression, and after I square it I get that, and I could combine the h's, so now I have the volume is proportional to the height cubed. Now I can take the derivative with respect to time of both sides. So on this side I will have the rate of change of the volume. On this side I have to work out the derivative of the h cubed, and this is what I get. All right. I really would like to see how the height is changing as I drain or fill it, so I'm going to isolate dH by dt. And if I've done this right, I get 1 over pi times the outer dimensions of the reservoir squared times 1 over h squared dV by dt. So the rate of change of height, the rate that the height is changing, depends both on how you're adding fluid to it and the height that the fluid level is already. That's what the h squared is doing over there. In fact, it's inversely proportional to that. Okay, here we go. Let's say that I'm going to drain the fluid out of this at a rate of 60 cubic meters per minute. And the tank is 25 meters high, and at the 25 meters its radius is 6 meters. All right. So I want to see how the fluid level is changing, dH by dt. I plug those numbers in and work it out. Actually, it turns out that it's minus 33.16 times h squared. The minus sign is because I'm draining fluid out of the tank. If the fluid is at the top of the reservoir, I would have to put 25 squared in the denominator. I find out that it's changing at about a half a meter per minute when I'm filling it at 60 cubic meters per minute. What if the fluid height is only, the fluid level is only at 5 meters? Then I put the 5 down here and find that it is changing at 13.3 meters per minute. And this makes a lot of sense. If you put volume into down there at the apex of the cone, which in this case is at the ground, the height is going to come up real quickly. If you put the same amount of fluid into the reservoir when it's almost full, you might not even see a change. So again, this is how to do these problems. You have an expression, and in that expression you have two variables, both of them changing with time, like the volume in the balloon and the radius of the balloon, or the volume in the reservoir and the fluid level in the reservoir. You try to eliminate any other variables with respect to time, so you only have two of them there. Use some geometry, algebra, trig, identities, whatever it takes to do that. Then you take the derivatives with respect to time of both sides. Okay, you'll end up with the first derivative with respect to time of both variables. You can solve for one or the other. And if you have a variable in there, you know that you have to, that the changes will depend on the height or the radius, or for example, how high the fluid is, or how much air you already have in the balloon. This is a pretty important problem. It's nice to solve it in general. We also could have solved it for the radius of the fluid level, but I think the height of the fluid level is probably a more useful parameter.